what we've discussed is special relativity. That's moving at constant velocity. Einstein worked that out relatively quickly and then spent quite a number of years later working on what we call general relativity. General relativity includes accelerated motion. And so the mathematics of general relativity are quite robust and well beyond the level of this class, but we can introduce some sort of hand-waving arguments and qualitative descriptions to how it works. And so that's what we're going to do. We're going to introduce it because this also turns out that general relativity includes the effects of gravity. That's where black holes really play into all this. Basics is the equivalence principle. Equivalence principle says that if you are moving at constant speed, there's nothing that can tell, there's no experiment that you can do that actually tells that you're in motion. It also relates to accelerated motion and gravity. And so that's how we're gonna refer to it right now. So the equivalence principle in terms of gravity is if you're in an accelerated reference frame. So for example, in the picture on the right over here, Albert Einstein standing in a box. If the box is moving upwards at constant speed, you're away from any planet or star, and you're in deep space, all you have is the motion of the box. You don't have any gravity. So if you've got an object you let go, it just floats in space. Now, on the left over here, Isaac Newton is standing in an identical box, and he drops something and falls down to the ground. Gravity made it fall. Well, back to Einstein on the right. If the box is not moving at constant speed, because if it's moving at constant speed, Einstein, the box, and then an object, an apple, or whatever he's holding when he lets go of it, are all going the same speed, and so it continues moving with the box and Einstein and floats wherever he lets go of it. This is what happens, for example, in the space station orbiting the Earth. An astronaut and the space station are all moving together, and so you let go of something, and it looks like it just stays right where you let go of it. Einstein, though, realizes that if the box is accelerating upwards, means it's going faster and faster and faster, when he lets go of that object, then it moves the way it was when he let go, but the box moves up faster and faster and faster until the bottom of the box comes up and hits it. Now, inside the box, it looks like the object went down to the bottom of the box, which is exactly what Isaac Newton saw in the left-hand picture. And so Einstein, via the principle of equivalence, looks at this and says any experiment you do in the accelerating box, you get exactly the same results that you do in the non-accelerating gravitational box. And so the acceleration is the same. And you say, well, how can it be? How does Newton know that he's got gravity pulling on him? Well, he experiences it as he experiences the force of the ground against him. If you're sitting down, you experience the seat pushing up on you, balancing gravity pulling you down. Well, in the accelerated box, if the floor of the box keeps going faster and faster and faster, then it has to push upwards on Einstein in the box here to make him go faster and faster and faster, just as the floor pushes up on Newton to balance the downward pull of gravity. And so it turns out to be identical. And so, again, if Einstein were sitting in this box right here, then the seat he's sitting on had pushing upwards on it to make him go with it. And so there'd be no way of doing an experiment that allows either of them to know whether they're in a box on a planet with gravity or a box in deep space that's accelerating upwards. And so that's the basic principle of equivalence. Now, how does that apply to what we've been talking about with relativity? Well, imagine you have a light source, like a laser beam, on one side of the box, and fires a beam of light across the box. Well, if the box is moving, that beam of light, when it reaches the other side of the box, is going to hit further down the box. Now, we know that from time dilation and so forth with special relativity, but if the box is accelerating, going faster and faster and faster, that means the path is going to be curved as it goes down and hits the other side of the box. Now, but every experiment that you do inside an accelerated box has to give the exact same result in a non-accelerated box, which means if you had a box sitting on a planet, gravity's pulling on it, which means that light going across would also get curved down. So that means when you have a flashlight or a laser or something, light actually is bent. The path is not really a straight line because it's bent by the presence of gravity. But wait, we know that light always travels in a straight line. Well, we get that, but then it's not because it's curved. So what does this mean? Well, this is actually an interesting experiment that was done. Shortly after Einstein predicted that this should happen, it turns out that there was going to be a solar eclipse. Well, the sun has a lot of gravity, so if you have a star out here in space, the light's coming towards Earth from the star, but if it goes past the sun's gravity bends it a little bit, which means if you look in the direction the light came from, it looks like the star's in a slightly different spot than it really is. Now, this would happen if light passes by anything with gravity, but the sun has way more gravity than anything else in the solar system. And so that's the only thing with enough gravity that they could measure at the time in the early part of the 20th century. So Sir Arthur Eddington in 1919, very shortly after Einstein makes this prediction, goes to where a total solar eclipse is visible, and the stars, the Pleiades, were showing up behind the sun, and they were slightly out of position with where they should be because of the sun's gravity. So this was the very first test of general relativity and the bending of light due to gravity. Okay, but light always travels in a straight line. So, so how do we compensate? I mean, how do we reconcile this? Well, what's a straight line? The straight line is the shortest distance between 2 points. Well, if you imagine on the Earth, you look at a map of the Earth, and an airplane flying across the Earth actually follows a curved path. Well, why? Aircraft are not going to travel a long distance because it saves money to go the short distance. Well, because a curved path on a curved surface is actually shorter. So if a curved path around the sun is, if light traveled in the shortest distance between 2 points, that means the curved path around the sun is shorter than the straight path. Well, how does that work? Well, there's this diagram here that's in almost every textbook about general relativity and gravity, and I both love it and hate it. What it's trying to show is that if light travels from here to over here, to one side of the picture to the other, if you follow what you would think is a straight path, you would have to go that distance, but if you follow the curved path around, then that's a shorter distance. And so this would indicate that gravity curves space in some point, in some way. And so that's what this diagram is trying to show, is that curved path on a curved surface is shorter than what would look like a straight path on a curved surface. And so light is following the shortest distance between 2 points, and that shortest distance is a curve because space is curved or bent by gravity. So that would be the idea. We refer to this as like a gravitational well, and then this in fact just gives us a whole new way of describing how gravity works. Is, for example, we got the sun, which has a big gravitational well, put a planet here, and it's going to experience a force rolling down to the lowest energy, so the deeper into the well. And so that explains how gravity works. Gravity says that general relativity says that space is distorted by mass, and then gravity is sort of this interaction of an object with the distorted space. Okay, and even something the size of the Earth would distort space. It would bend space near it, though this would be a much smaller effect than the space being bent near the sun. In fact, this is actually measurable in modern tools. We can measure the distortion of space. We now have ability. In astrophysics, we look at distant objects. For example, a galaxy is even bigger than a star, like the sun. And so we would have a really distant object called a quasar that's right behind a galaxy, and the light would be bent. So if you look at it here, it would look like the quasar is there, or look like the quasar is here. And this would happen with a black hole. The light would simply be bent around the black hole. The black hole is not necessarily black, but it bends light around it. So again, this is what we call gravitational lensing, the bending of light by gravity. We've confirmed that too. For example, on the left here is a galaxy right there, and those four dots there are all the same object. It's one object that's behind it, and the light's being bent around, and so you can actually see that one object in four spots there. On the right over here, you see these mysterious little arcs of light. That's actually due to an object that's on the other side of that galaxy cluster, and the light's being bent around and being bent into these arcs. So that when you look at it, you don't see the object, you see light stretched out by the gravity, and you see these arcs that are coming from the light of the object.